morning, friends. We have been doing so many activities. We try to understand what is static stability. We try to understand how to trim a particular aircraft at a particular CL or CL trim. We also understood the significance of neutral point, fixed neutral point. And on the stability aspects, we have solved one problem. And as I promised, that we'll have a session where we'll be more focusing on how to implement whatever we have derived in understanding delta required, or how to calculate Cm naught, how to design an airplane to have a particular Cm naught, what should be the elevator deflection required to trim an aircraft while it is climbing, while it is cruising, while it is landing. We also know what happens when the aircraft lands and very close to the ground. With this background, we will try to solve one or two examples, maybe one example in detail today. So before I solve a problem or I discuss a problem, let us again revisit few basic understanding. This part is climb, this is cruise, and this part is landing, all you know. Now, when I am climbing, what happens? This is the wing, this is the CG, this is your mg acting here on the weight, and here it is drag, here it is thrust, here it is lift. We have assumed that the thrust axis is along the fuselage reference line. We are also neglecting the angle of attack, or not neglecting, we are saying the angle of attack is small. Okay. And we are trying to develop a model for steady climb. Steady climb, so no acceleration, right? It's just going like this, rectilinear motion, like this. So if I use this diagram, I know this is gamma, the flight path angle, and then if I want to ensure that this plane is going in rectilinear direction, in this direction, then net force on the body across this line should be 0. So no acceleration here, no acceleration along this, no acceleration along perpendicular to this. We are assuming the airplane is moving in a vertical plane. Okay, right. So if I do that, then I find L should be equal to mg cos gamma, because steady climb. Steady climb means you know that L minus mg cos gamma should be equal to m into acceleration in the perpendicular direction. But this we are putting 0 because it is going in rectilinear motion and unaccelerated, steady climb. So L equal to mg cos gamma, or which L equal to w cos gamma. And what is L? L is nothing but half rho v square SCL, half rho v square SCL. So I get CL equal to w cos gamma by half rho v square S. This is my CL climb. Okay. So we are trying to model, or we are trying to ask a question: if this airplane is to remain in this rectilinear path, then what should be the CL with which I should fly? And if it is supposed to be in rectilinear path, then the forces along this path and forces perpendicular to this path should be balanced, or net force along these two directions should be 0. Okay? And in this case, please remember, what we are asking is, this is fine. This diagram tells you what CL I should fly. But what is our question? Our question today, we have become mature enough to ask another question, is for this airplane, fine, this should follow rectilinear path, but it should be trimmed. So trimmed means not only these forces should be 0, but it should have net Cm 0. Okay, that is what we call as the airplane is at trim. Okay, that is this point Cm is 0. And what is the CL? The CL is CL climb. And how do I find CL climb? I use this relationship. What is my next question? Is what is the delta E required for this climb? Is this question clear? Fine? Right? Now we will just formulate a problem to solve this, and you will very well understand what I am talking about and what is the relevance of this example. We know that delta E equal to delta E naught plus d delta E by dCl trim into CL trim. Okay? And what is d delta E by dCl trim? Is nothing but minus dCm by dCl by Cm delta E. Right? So let us take an example. Let's say weight is 1000 kg of the airplane, right? Assume V is equal to 100 meter per second. This is the climb speed, okay, which is very high, but I'm for numerical advantage I am taking 100 meter per second. And let's say rho is 1 kg per meter cube. If it is at sea level, it will be 1.225, something like that, but I am taking 1 kg per meter cube, and S I am taking as 10 meter square. Okay? These are my input. Right? So what is the CL required for climb? You could see from here. I'll erase this part. So CL climb will be how much? Will be W. W is 1000 into 9.8, because this unit should be in Newton, it is in kg. So I am taking the value of G as 10 meter per second square. No problem. So I put it 10, which is nothing but value of G, which is typically 9.8, 9.79, depending upon the location. But for computational simplicity, I am taking as 10 meter per second square. So W, then half is 0.5 into rho is 1 into V is 100 square, 100 into 100, and into 10. 10 is your area. So how much it comes down to? 1, 2, 3, 4, 5. Point is going there. So here 5 into 2, 2, 4, and 5. 1, 2, 3, 4, 5. 2, 2, 4, and 5, and 0.5 has gone here. So this is 1, 2, 3, 4, 1, 2, 3, 4, and for 0.5, this becomes 5, right? Here also 5, so this gets cancelled. So I am getting CL climb equal to 1 by 5, and that is equal to 0.2. Correct? So I have to fly at CL equal to 0.2. So what is the next question? What is the delta E required to trim the airplane at CL equal to 0.2? How do I find out? So now I know what is delta E naught is minus Cm naught by Cm delta E. So for this aircraft, there should be a fixed value of Cm naught and Cm delta E. So let's assume Cm naught equal to 0.05 and Cm delta E equal to minus 1.0 per radian. So if that is the value I am assuming, which are typical values for an airplane, so delta E naught will become minus 0.05 by minus 1.0, this is equal to 0.05 radian. Please understand, this is radian because Cm delta E is given per radian. in many problems you will find Cm delta E may be given in per degree. So then delta E naught will become in degrees. Okay? So you should be very, very careful about the unit. Whenever these things are coming, check. Unit is per radian or unit is per degree. Okay? So Cm naught is this. Now d delta E by dCl trim I want. So further, let's say dCm by dCl. You remember dCm by dCl is given as minus static margin, and typically let's say the static margin is 10%, so it is 0.1, so this value is minus 0.1. So what is the static margin? The airplane is having static margin is 10%. Okay? That means the difference between neutral point and the CG is 0.1 into C bar, mean aerodynamic chord. Okay? So I know now, you see, for dCm by dCl, the value is minus 0.1 and Cm delta is 1. So what is d delta E by dCl trim? Let me write it here. So d delta E by dCl trim equal to minus of minus 0.1 divided by minus 1.0. So this is equal to minus 0.1 radian. Please note that here also dCm by dCl, then Cm delta is per radian. So this becomes radian here also. The unit is radian. So now what is delta E required? Delta E required will be delta E naught, that is 0.05 plus d delta E by dCl trim is minus 0.1 into Cl trim is 0.2. So what is delta E required? Delta E required will be delta E naught, which is 0.05 plus d delta E by dCl trim, which is minus 0.1 into Cl trim is 0.2, right? So this becomes 0.05 minus 0.02, and this is equal to 0.03 radian, and which is approximately, you can see 0.03 into 57.3, this is degrees, right? So that will be around 1.8 degrees, correct? So that much of elevator deflection is required to trim the airplane during climb, which is climbing with CL equal to 0.2, correct? Okay. Now see, if I want to solve a problem, this problem little differently. Now if you want to solve this problem little differently, the information could be, instead of given static margin 10%, the information could be given like this. The XCG, the airplane is at 0.5 or let's say 0.3, and neutral point power on is at 0.4, and also it could be given neutral point power off equal to 0.045, because you know power off is more stable compared to power on. We are assuming that engine, whether it is a propeller driven engine or a jet engine, they are ahead of CG. Okay. So if information is given like this, if static margin is not given directly, then you can easily find out dCm by dCl, which is equal to minus static margin, which will be equal to minus of, how do you define static margin? Is a N naught minus XCG bar. Now the question will come, which N naught you will take? N naught power on or power off? Obviously, it's an airplane with an engine. So when it is climbing like this, power is on. So I'll pick this N naught. So I'll write minus of 0.4 minus XCG 0.3, right? So this will be my static margin. So I can solve this problem into different ways depending upon what information has been given to us. Okay? So this is for the climb. Now we will do the exercise for cruise phase. Okay, let's come back to the cruise. Let us solve this problem for cruise case. Let us see, I say the cruise speed is 100 meter per second. I say rho is 1 kg per meter cube, that is at an altitude which is little higher than sea level altitude. And of course, same airplane is 10 meter square, right? So when I am talking about cruise, I can ask a question. I want to cruise such that thrust required is minimum. Okay, I can cruise such that thrust required is minimum. One, and I can also question thrust required is as driven by altitude. I'll explain both the problem, we'll solve both the problem. So thrust required minimum, the moment I want to solve this problem, what is my question? Question is, what is that elevator required to ensure that the airplane, when it is flying at an altitude where rho is 1 kg per meter cube and cruise speed is 100 meter per second. So what is that elevator required to trim the airplane with this condition, right? So now once we are talking about thrust required minimum, that means CL equal to CD naught by K. I hope you remember this. Those who do not remember, for them, for a cruise flight, for a cruise, thrust equal to drag, lift equal to weight. So this implies thrust equal to W by L by D. This equal to W by CL by CD. And that means thrust required minimum if for a given weight CL by CD is maximum. And you know that the condition which we get from drag polar, that is CD equal to CD naught plus KCL square, I can show that for CL by CD to be maximum, the condition is CL equal to under root CD naught by K. Okay, so now if I want to trim the airplane in a cruise so that thrust required is minimum, it tells me the CL cruise should be given by CD naught by K. Now there will be a conflict if we prescribe what is the speed and we are telling what is the CL cruise. Now see, that's why this problem I have formulated. The moment I have to fly at thrust required minimum, the CL cruise is fixed. Why it is fixed? Because for an airplane, CD naught and K are fixed. For example, CD naught, let's say for this is 0.02 or let's say 0.02, and K you can find out, let me say it's 0.5. So you understand that if I want to fly such that thrust required is minimum, then CL cruise will be given by CD naught by K. Let's take for this airplane, CD naught value is 0.020 and K is 0.02. So then CL cruise we are getting as under root of 0.02 by 0.02, and that is 1. Pretty high, but for numerical example this is okay. The point what I am trying to tell you, if you decide altitude, right? If you decide I want to fly such that thrust required is minimum, that means CL equal to CD naught by K, then that means this is, and CL is fixed because CL is CD naught by K, then you cannot keep cruise speed arbitrary. It cannot be just 100 meter per second. This has to be corrected. The cruise speed possible at that altitude to maintain thrust required minimum, which gives CL fixed, the VC will be, or the cruise speed also will get fixed by these two conditions. How? Because after all, at cruise, lift has to be equal to weight. Right? So, lift will be equal to half rho V square SCL, that should be equal to weight. So, V will be equal to 2 W by S by rho CL. And what is this CL I will take? So, this becomes V cruise. What is that CL I will take here for thrust required minimum? This will be this CL. This is CL for thrust required minimum. That is 1 for this example. So, I find V equal to 2, W is how much? W is 1000. So, 1000 into 10, value of G, approximately you have taken, divided by S is 10, rho is 1 and CL is 1. Okay, 2 W by S rho CL. So, this gives me how much? This is of course V square equal to, right? So, V square equal to this. So, this is this 10, 1 goes here. So, this is under root of, so V will be equal to under root of 2000. So, this is typically equal to 10 root 20, and root 20 could take around 4.2 or 4.5. So, this will become around 10 into 4.3, so around 43 meter per second. Right? If my calculations are okay, so it is around 40 to 45 meter per second cruise speed. What is our observation? We said that to fly at thrust required minimum at a given altitude where rho is 1 kg per meter cube, then what V you have to fly will be governed by this relationship, which comes from lift equal to weight, and that is 2 W by S rho CL, and CL corresponds to CL equal to CD naught by K. So, once you have fixed rho and once CL is fixed from the condition thrust required minimum, then the V cannot be arbitrary. V will be driven by these two values for a given wing loading, right? So, and incidentally for this case, V is coming between 40 to 45 meter per second. Second problem is, you fix rho, right, and you fix V. What was fixed here? Here rho was fixed, CL was fixed, right? Repeat, rho was fixed because the altitude was fixed, which corresponds to density 1 kg per meter cube. CL was fixed. How CL was fixed? CL was fixed because CL has to correspond to thrust required minimum, which is given by CD naught by K under root. So, first case, rho and CL was fixed. So, naturally, since you are cruising lift equal to weight, the V automatically get fixed. So, that becomes V equal to around 40 to 45 meter per second for this example, right? But for the second example, if I say I keep rho fixed and V fixed, clear? I want to cruise at 100 meter per second at altitude where density is 1 kg per meter cube. So, this also will give me what is the CL cruise required as 2 W by S by rho V square, right? If it's 100 meter per second, put 100 here, rho value W by S put here, you will get a CL cruise, any altitude, but it is not necessarily CL for thrust required minimum. For CL for thrust required minimum, your V has to be related to rho and CL because you are not changing the altitude. Now, this is what the CL concept. Now, what is our main aim? I want to know what is the delta E required for, let us say, CL corresponding to thrust required minimum. Okay? And we have seen, we have just now seen CL required for thrust required minimum is 1.0. I repeat, this is higher value. Because of numerical convenience, I have taken some values, but typically CL cruise at an appropriate altitude for our jet-driven airplane and all, which flies at around 11 kilometers, around 11 kilometers, CL cruise will be 0.2, 0.3, not more than that, right? But this is an example. So CL required is, or I will say CL trim is 1. So you know delta E equal to delta E naught plus d delta E by dCl trim into CL, and this equal to delta E naught. This value also you know, and this is minus dCm. We are trying to find out what is the delta E required to trim the airplane at CL trim equal to 1.0, which corresponds to thrust required minimum during cruise. So you know delta equal to delta E naught plus d delta E by dCl trim into CL trim, which again I can write as Cm delta E into CL trim, and this equal to delta E naught plus minus dCm by dCl means this will be N naught bar minus xCg bar by Cm delta E. Okay, this is cruise. So N naught bar will take from here, power on 0.4, and every numbers I know, so I can find out what is delta E required. As simple as that. The trick was, what is the CL I need to trim? Right? If it is CL for any other combination, that CL has to be put for cruise. So this is into CL trim, and CL trim is, you know, it is 1 in this case for this numerical we are solving. So I'm sure you will be able to complete this. Now the question comes, suppose it is now coming for landing. Let's say it is coming for landing, and I am without ground effect. Okay? I am solving this problem without ground effect. That means for a distance which is ground distance is more than 1 to 2 span of the airplane. So without any ground effect, because you know with ground effect I have to give additional delta E. So we are not talking about that. So then again the delta E will be equal to delta E naught plus dCm by dCl minus here Cm delta E into CL trim, and this again equal to delta E naught plus N naught bar minus xCg bar by Cm delta E into CL trim. So what will be the CL trim required for coming for landing? That will be again governed by same, it's coming like this, it's just follow rectilinear path. So it will be again the way we solve for climb, we have to solve like this, same equation will come. So you can easily find out CL trim. Only point would be what N naught I should take. So I'll come back to this. But physically see what happens when I'm coming for landing, I'm actually trying to land at a lowest speed possible, right? Little more than the stall speed. So I increase the angle of attack and reduce the speed and start landing. Okay. So the CL, that is very high. So CL could be around 0.81 during landing, 1.2. Theoretically we talk about 1.2 for normal airplane, but it's safer to land at 0.8. That's good enough value CL. But the question is, when I'm landing like this, I have two ways I can land. One is, theoretically speaking, I put the engine off, okay, and land like glide mode I land. It's coming like a glider, it's descending like a glider. Or I keep the engine at 10%, or I have not locked the propeller. So when it is landing, because of windmill effect, you know, the wind is rushing because relative air speed, and the propeller will start rotating, and that will generate some thrust. Okay, typical windmill examples, which are of a life-saving concept for helicopters, right? Okay, so you must do a net surfing and read more about windmilling, right? So the question what I'm asking is, what N naught should I take for landing? And when I'm thinking about landing, definitely the thrust is not fully on. It could be 10%, 20%, or windmilling. So if you have switched off the engine, typically gliding phase, then you have to take N naught as N naught power off, 0.45, whatever value is given for the airplane. So I will take N naught bar as 0.45 in this example if during landing power is off. Rest everything remains same. But if it is, the pilot has initiated windmilling, that is, he has not put the brake on the propeller rotating because the relative wind is coming and some thrust is being generated, then this N naught should be propeller windmilling. And that value I need to have, so let's say that value will be propeller windmilling. Typically that value will be in between 0.4 and 0.5. What is it? You see, this is power on N naught. This is N naught bar power on. This is N naught bar power off, more stable. So propeller windmilling will be between this and not windmilling. Okay. So between these two numbers, it will be around 0.42. Point is, whatever the number be, you need to understand N naught for propeller windmilling will be between these two somewhere. And when I'm calculating delta required for landing, so I will be taking N naught corresponding to propeller windmilling. We will not take N naught corresponding to power on. Is it clear? That is what you should be very, very careful. Okay? Thank you very much.